Good morning, everybody. Neil is unavailable this week, which is why you've got me. In today's lectures, I'm going to talk about simulation software. This will be useful for the tutorial sheet this week, which is already on Blackboard. It'll also be useful for your assignment, which, if it's not on Blackboard already, will be coming up very soon. So up to now, we've studied systems, control systems. We've looked at, we've gone through trying to model a system, trying to work out how we represent that system in transfer functions. We've done some analysis looking at the time domain. We've done some analysis looking at the frequency domain. Okay. We've also looked at various ways that you can modify a system. And the week before Christmas, Neil started talking to you about control systems, okay, and how we design controllers. And we looked at proportional integral derivative control and variations on the theme. So we understand how to model systems, predict behavior, and how we can design some controllers. Okay, we'll now look at some simulation techniques using software. Now often when you're, as an engineer, you'll no doubt be designing and coming up with things and prototypes and stuff. And often before you build something, you want to look at how the system's going to behave. So you try and model it, and using the software, you can then do some analysis based on that model and work out some predicted results before you actually build anything in hardware. And then obviously what you can do is you build a prototype in hardware, you take some tests, you can compare the results, work out where there's differences, and if the hardware matches the model, you can then validate the model, and you can make improvements on the model before you do so in hardware. And it's just all part of a design process. And there are many software packages out there that will enable you to do this sort of thing. Industry standard is, well, one of the industry standards is a program called MATLAB, and it's sort of accompanying package called Simulink, which we'll look at in a bit more detail. So MATLAB and Simulink, they're the basis of what this lecture is going to be about and what you'll be using in your tutorial and your assignment. So what is MATLAB? Well, MATLAB is a package developed by the MathWorks, which is a software company, okay, and it was originally designed quite a long time ago to deal with matrix algebra. Basically, it's a big calculator, runs on the computer, and matrix laboratory is obviously the reason why it's called MATLAB, okay, and became MATLAB. And because it's been used, it's used in industry all the time, and although it runs in like a command line interface, you can actually write programs in it using a programming language, called MATLAB. Okay, it's like any other programming language, but it's very it's relatively straightforward to program. It's not that difficult. Okay, and like I said, because it's a command line interface, you can enter commands in one by one as well. Every step of the way. And I'll give a short demo of MATLAB right now. So this is MATLAB. This is the main window. Okay, this is the main command window. You've got this is obviously a library of files. At the moment, I'm in the bin folder. Okay, there's the command window with the prompt. Over here, the workspace. That contains all my variables, and then down here is a list of commands that have been run on this system before. Okay, and so for example, if I want to, I could do very simple calculations. 2 plus 3 times 4 is 14. Okay, obviously it follows order of operations. Okay, and like I said, you can come up with a magic makes a magic square. I don't know whether you know what a magic square is. Magic square is this is a function, and obviously that's the operator of the operand of the function. And the magic square basically have made a 4 by 4 matrix. Okay, and each of these columns and each of the rows, and even this diagonal, all add up to the same number. So what have we got? 25, 34. Is that right? 10 plus 11, that's 21, plus 13, yeah, 34. Okay, so that's a magic square. And that's a matrix, and you can do all sorts of things like that. If I set A to be that magic, that matrix, magic 4, okay, so there's A, and I can do transpose A, okay, you can do A times A, that's a cross product, okay, and if you wanted to do the dot product, you do dot A. Yeah, so there's all these different commands you can do to multiply and matrices together and stuff like that. Okay, so this is MATLAB. To give you a little taste of the power of what MATLAB can do, I have on my stick yesterday I went to a sort of a special interest group day revolving around bloodhounds, okay, and how we're going to implement it in education. And at this day was Ben Evans, who's the basically he's done all the aerodynamics for Bloodhound. He works at Swansea University, and he was showing us this, which is a basically this is MATLAB. This is a command window. Like I said, that you can enter stuff line by line, or you can actually make a program. And what he's done is made a program. There's a couple of special functions that he's developed. There's that one there, calculate mission profiles, imperial mission profiles, and then plot mission profiles. And they're actually in that folder. If I go to that folder, let me. So where are we? Let's keep going back. I think it's F, yeah. So there are those profiles. You see calculate mission profiles. And you can see that the icon is a function. That F and X thing is a function. So that program that he's written calls those functions. And what you can do is if I run the program, so what I've produced is 4 plots. Okay, this is all about Bloodhound. If I, let's see if I can. Essentially this plot, okay, figure 1, this is time along the bottom, obviously, and this is how fast Bloodhound goes. And you can see that after 30 seconds, we're going through the measured mile at just over 1,000 miles per hour. Okay, so Bloodhound's not been made yet, but they've done loads of calculations and looking at the drag and the forces and when you fire the rocket and all that sort of stuff, you can get the velocity profile. This is the distance profile, okay, versus time. So it's going to travel 12 miles in about 90 seconds. And then we've got acceleration profiles versus time and acceleration versus distance. And this is in feet per second squared. Okay, bear in mind that 32.2 feet per second is 1 g. And look at the acceleration that Andy Green, the driver, is going to experience as he fires the rocket. We're up to 80 feet per second squared. So there's 1 g, okay, about 30, and he's going to experience sort of 2.5 g. It's quite big accelerations. Okay, so that shows you the power of MATLAB. That's a program that I've just run in MATLAB, and it's produced these graphs very quickly. So if we go back to the presentation. Okay, so like I said, MATLAB, very powerful, and you can enter it in commands. You can also enter a program, like a program file. And this ability to make their own programs has led to the development of lots of specialist functions. Some of them are created by MathWorks, the people that make MATLAB, and there are third parties that have also made specialist functions in parts of MATLAB. Now, the specialist functions are arranged in what are known as toolboxes, okay, and they're suited to particular disciplines. One of which is control engineering, and that toolbox is called the control system toolbox. Funny enough, so I'll give you a quick demo of that. So here I am I'll just clear the screen. So here I am with my command window, and it looks like the last person to use MATLAB was here because I'll be entering these commands. So I've got a control system, I've got my transfer function, and what I'm going to do, if I say the numerator, I'm going to enter the coefficients of the s values of the numerator. Now let's say I've got no zeros, so I'm just going to enter 1 to give me 1 on the numerator. And in my denominator, I'm going to have a second order system. So I'm going to enter 1s squared plus 1s plus 1. Okay, so there's two vectors. Now there's a special function in MATLAB, okay, called TF, which makes the transfer function. And so I'm going to say my system equals transfer function of the numerator and the denominator. Okay, and what this is going to produce is a thing called sys, which is a transfer function with 1 over s squared plus s plus 1. Now that MATLAB knows about my transfer function, I can do various commands like bode, it's working on it, busy, there we go, it's much quicker. And there's a bode plot of that system. Yeah? That was quite nice and easy. Let me put the grid on. So there's my bode diagram. Okay. Now what about if I reduce the damping? If I make the denominator, let's go for 0.31. Okay. And then I run the same command again, and the same command again. You saw that bode, you reduce the damping, you get this sort of peak appearing. And if I made the damping bigger, it would turn into what looks more like a first order system. Okay. So that gives you an idea of the control system toolbox. And you can, MATLAB, one of the big things of MATLAB is its help system. Okay. And there's so much information in there, and demos and all that sort of stuff. So it's a really good resource. You can actually go to help. Tells you about it. There's also big resources on the internet that you can refer to as well. So this is just a taster of what the control system toolbox can do. Obviously, if I wanted to do the Nyquist diagram, I could do the same thing. I've got a Nyquist diagram for that system, that transfer function. Okay. So that gives you an idea of the control system toolbox. Let's go back here. Okay, so that's the demo. Now, Simulink. There's a slightly different set of tools called Simulink. That's part of MATLAB. Okay. And Simulink is a graphical user interface that allows you to just basically build a block diagram as you have been doing by hand. Okay. And once you've got that block diagram, you can run the system as a control system. Okay. And once the system's modeled in Simulink, it's possible to run simulations of systems and visualize any of the parameters of interest. And so I'm going to do a demo. Well, I'll show you. This is a Simulink window with a sample system. Okay, we've got a step input, a summing junction, a transfer function, and then scope is basically the output of a graph. Okay, you can output it to MATLAB as a file, or you can output it to Excel, all this sort of stuff. Here we're just outputting it to a scope. So I'm going to very quickly make this system in Simulink. To get to Simulink, you see the button up there, the colours. Okay, that's Simulink. You click on it, and it opens Simulink, which is, like I said, a different set of is a part of MATLAB. You don't use the command window in the same way. Okay, so it takes a little while. It's just booting up. Okay. So here's our library, and I'll make a new file using the new button. Okay, there's my new Simulink window. Now in the library, there's various things that you can use. Okay. For example, I've got math operations, so I can. There's loads in here, but obviously that's a summing junction, add. I've got down here a gain I could use. So you've got product down here, okay, multiply things together. Sinks are where signals go to, so there's my scope, look, okay, or my terminator, or like I said, to workspace as sim out, or to a file, saving as a MATLAB file, or I can display a number. Sources is what signals originate from, so we've got things like a step input, or a sinusoid input to do frequency analysis, or ramp, or you can make your own signal builders, and you can make your own inputs and outputs, okay? There's even a clock to give you the time. Now the thing that's important for you guys is this continuous library. And in here, you can see this one here is a transfer function, okay? There's a derivative up there. It's quite difficult to derive mathematically, but integrating is much easier. Okay. And there's various other. Like I said, you can see there's absolutely loads and loads of blocks that you can use. So let's make that little system that we had before. So I'm going to start with a source. Let's go for a step input. Okay, so you just drag it from the library onto the window. Okay, let's go for a transfer function. There's my transfer function. And let's go for an output sync, so scope. And you connect all these up either just by dragging or you can just click on one and then control click on the next one and it will connect them for you. Okay, so there we go, very simple system. Step input to a basic first order transfer function, and we're going to output into the scope. So I press run. It's going to run for 10 seconds, which is this 10 here. Done. That's my output. Okay, you can see that's the first order system. At 1 second, the input said, okay, I'm going to go from 0 to 1. Nice and basic. And what I can do, just to complicate it a bit, to make it easier to see, signal routing, let's go for a MUX, one of these. So I'm just connecting these up, and I'm going to take the input before the transfer function and also put that on the graph. So now if I run it, you can see I've got my input, which is the yellow line, and my output, which is the purple line. Okay. Now there's various other things I could do. I could make this a second order transfer function by adding another S in here, and then I'm going to reduce the damping to be 0.1. The damping term. So I run it again, and oh look, with a second order system with extremely low damping, I get an oscillatory result. Okay, I can obviously change that damping term. Let's go for 0.5, say. Run it again. And there we go, another damped result. Okay. Obviously, I've just increased the damping a bit, and obviously that's reduced the amount of oscillation you get. And you can enter various other terms and stuff like that. Let's go for a closed loop system. So I'm going to delete this. I'm going to add a math function of adding. So let's put that in there. Let's make it a circle, because we like circles. I think it's going to be a plus and minus, negative feedback. Okay, so my step connects there, that connects there. I've got this one. Oops. So it's got a feedback loop in here, okay? And we'll take the input and put that in the scope as well. So you can drag around these things. So here I've got my closed loop system. I can, I could have rotated that if I wanted to. There's ways of doing this, depending on what you stick in here. Okay, so that's now. There we go, that's a bit easier to see. So here I've obviously got my input, summing junction, for transfer function, feedback loop, yeah, okay. And then it's going to my output, and I can compare it with my input. So if I run the same thing again, you can see that adding the feedback loop has given it a steady state error, okay. So if I make this 30 seconds, you can see that I've got this steady state error occurring between the input and the output. And so I think, well, perhaps if I increase the gain, so I bring the gain in here, let's drag these out a bit so I can fit the gain in. Let's just drop the gain on there. Let's give it a gain of 5. So that should increase the response time, which it has done, but it also increases the oscillations. Before, the oscillations weren't even going outside of the input, but now we're obviously breaching that. It's reduced the steady state error, which a gain would do, up to a point, but obviously it's increasing instability, and so on and so forth. So that's Simulink. Okay, and that's basics of Simulink. You have this library browser with all your different commands in, and you just drag them onto a Simulink window and arrange them, connect them up with these signal lines. Okay, like I said, transfer function, gains, math operations, inputs and outputs, and you've built your transfer function, your control system in a block diagram form, which is the way that you've learned how to do it by hand. So that's a demo of Simulink. Okay. So like I said, this was just a basic first order system, and you build it by using blocks and signals, joining them together. I gave you the demo, and this is the sample sort of output of Simulink. Okay, and this is an output of that previous one. And as you saw, with the closed loop, you end up with a steady state error, and so you can. And obviously that's what's being shown here. The input is 0 to 1, and we're coming out with about 0.5. So, it's quite a short lecture today. That's it. What's going on? Well, now that we can describe systems using block diagram techniques, we can use software to simulate our block diagrams. Okay. If we're designing a controller, for example, we could use the tool to verify our values for, let's say we're using a PID control. We can verify our proportional gain, our integral gain, and our derivative gain by looking at the output, and then before you actually implement such a system in hardware. And like I said, there's loads of resources when you're working through this stuff. If you Google MATLAB or the MathWorks or MATLAB and then the problem you're trying to solve, there's absolutely tons and tons of stuff on MATLAB. There's all sorts of various different things. And like I said, you can use it as a big calculator, okay, or you can use it to simulate a power station. It's that complex. You can make it as complex or as simple as you want. Okay, it's huge. And so, as I showed you, there was a simulation of the Bloodhound car, which is like a jet fighter with wheels. It's extremely complicated. Aiming for 1,000 miles an hour, that's Mach 1.4. So it's all sorts of horrible compressible flows and things going on, shock waves and drag. Okay, so this is what MATLAB can do, and it's hopefully you should enjoy using it. That's it. Thank you very much.